So we have one more problem to do relative to mass moment of inertia. It's sort of our ultimate problem here. And that'll finish this chapter up. So what I have here is a really big disk, 8 inches high, 10 inches in diameter. At 150 pounds per foot cube, this thing's pretty heavy. All right, of course, this is specific weight. If we divide by 32.2, we would have the density, which we're going to need mass. That's going to be relevant. So let's take a look at this really big disk that we have. And what we have in the disk is somebody has gone in and has machined in sort of another torpedo tip, you might say. So this is 6 inches in radius, and then as you go down, the radius drops down, and this goes all the way to the bottom of the disk. And as we take a look here, we see if we look in this XY plane, this outer part, there's the equation. So if you're going along, if you could just do a slice here to get the XY plane, this would be the equation of the cutout that you would have, the edge of the cutout. And so what we want to get for this problem is IY. And that makes sense because if you kind of look at the symmetry relative to the y-axis, it looks like if this thing were going to rotate, it would kind of go like so. It'd be in the y-axis. So that seems to fit. All right. So we're going to do this two ways. We're going to do it by the shell method, and we're going to do it using a differential inertia. Now, with respect to the shell method, what we would have is, let's just kind of look from the outer end. So the outer shell would be radius of 10 inches and height 8 inches. And then we just let the radius get smaller, smaller, smaller until it got to 6 inches of radius. And that would still go 8 inches down. But as we took our shells further and further and further in, the height of the shell, because of this cutout, will start dropping till it gets down to 0. Okay, so let's take a look at this. So our shells are going to be like so, with this height, and of course thickness would be, we'll call dr. So here's your basic shell differential volume. 2 pi r, the circumference. So you're going to go out some r to get to the shell. Circumference times height. We'll start out at 8 inches, and as we go in, it'll go down to 0. And then the thickness of the shell, dr. All right. So I'm rotating around y. What makes sense? It makes sense for our radius to go in the x. From 0 out to 10. Whoops. All right, so IY would be r squared dm. So we're going to integrate relative to the x, so we'll let r be x. The height, in this range it'll be 8 inches, but then as we get inside r is less than 6, the height will come from here. Y equals 2/9 x squared. So h equals 2/9 x squared. Or it equals 8 if the radius is greater than 6 inches. Okay, so let's move. I'm going to move this down. So let's use that. IY is r squared. We're letting r equals x. So there's the x squared. We need differential mass, so there's volume, or density. I'll just put the rho in there, times differential volume. 2 pi x circumference, 2/9 x squared for the height of this thing. Notice here we're going from 0 to 6. So inside the cutout, this would apply. Here's the height. And then dx is the thickness of the shell. Now, we need to get from 6 to 10. So as we integrate from 6 to 10, we have the x squared, we have the rho. 2 pi x is still the circumference. Now the height is just always 8 dx. This is a straightforward integration in x. If you do that, let you check the numbers, you'll come up with 324.1 slug inch squared. All right. So when you do this, you're going to be this row is going to be 150 divided by 32.2. Now, that would be in slug inches, because notice we were going in inches, 0 to 6, 6 to 10 inches. If we divide by 144, we would then have 12 inches to a foot. So if we divide accordingly, that would leave us with 2.25 slug foot squared. So that's the shell method. It was really straightforward. Just people have a little trouble getting their heads around these shells at first, but once you get used to it, it's pretty quick. All right, so we're going to do this again, and now we're going to use discs. So let's start setting that up. We'll drop this a little further. So I'm going to use differential discs that are dy thick. So what I'm going to be setting up here is, let's go here, to compute IY, I will have differential IYs. That implies that whatever I have, as I go, I'm going to be integrating along the y-axis, which says I'm going to be using things that are dy thick. All right? So that's what I see here. I'm going to have to lose my picture here for a moment. Let's see. So we'll come down. So let's work with this. It's a little smaller. Hope you can handle that. So the differential inertia, so DIY, so it's dy thick, are just going to be a disc. It's going to be a disc with a disc hole in it. So here's an outer one, and then here's a hole. So when we go up here, if we did a thin disc along the top edge, it'd be a donut. Okay, we'd have an outer edge and an inner edge and then a hole in the middle. So we're going to be making donuts. And as we go down, the outer part will stay the same, but this inner hole is going to get smaller and smaller and smaller until the end it disappears. All right, discs, very easy. They're 1/2 mr squared. So 1/2, the outer disc radius is 10 inches, minus whatever this, remember we had radius was x before, so this is r squared, so that's going to wind up going from 0 to 6, dm. Okay, now the problem is our thickness is dy, so we have to integrate into y. It means we've got to change this x into a y. Well, that's very easily done. We have that equation. Y is 2/9 x squared. All right, solve for x squared. 9y over 2 is x squared, so we're just going to stick that in here. So that'll solve that. Then we have our differential mass. We have to express that in terms of dy. All right, so let's make that happen. So differential mass of relative to the outer ring, so that whole big circle, we're going to have density times volume. So rho times, so if you picture that outer circle, what's its volume? Pi r squared, pi 10 squared, dy is the thickness. That is what goes in here. Now we have dm2. Same idea, rho, pi x squared, because remember before we had rbx, and dy thickness. So once again, we just take this x squared and we replace it with this term right here. So now we have pi rho 9 over 2y dy, and we just stick that all up into there. So if we do that, let's just take this up and we'll get to the math. And that's what we have right here. All right, so IY, we're going to go from 0 to 8. So we're going from the bottom, let's just bring this back real quick, integrating from the bottom here up to the top. So integral 0 to 8, and we have our 1/2. This is r squared. Here's dm1. Radius is 10. Then we also subtract off from 0 to 8. These are our holes. 1/2. Okay, r squared, which is x squared, is simply 9 over 2y. Mass, rho pi r squared, 9 over 2y again for the x squared, thickness, dy. Now you simply have to do the computation, and if you do, you come up with the same number, 324.1 slug inch squared, or 2.25 slug foot squared, and this problem is put to bed. That finishes up our mass moment of inertia, and we will be back at you. This finishes up the first 3 topics of the course based on how I would put things together. We've had momentum, we've had centers of mass, volume, and we've had now mass moment of inertia. So this means it's time for our first midterm. We'll talk more about that later. Bye.